Our final project for this class is going to analyze an autonomous cable-driven parallel robot for cleaning skyscraper windows. This is a project by Becca, Karthike, Heather, and Nihar. Window cleaning is dangerous for humans, and the robots that currently exist to replace them require expensive rail gantries or depend on unreliable suction systems. As buildings get more complex, it also becomes more difficult to reach all the surfaces. We therefore propose a cable-driven parallel robot that can clean large areas and complex building shapes without requiring rails. The three main areas of research have analyzed the holding equipment, moving equipment, and cleaning unit. Major research has been done and various holding equipments have been considered over the years, but many design prototypes have considered the suction mechanism as a feasible solution because of its versatility and reliability.
Our window cleaning robot is a lightweight platform which is suspended from two cables. It consists of a pair of cleaning brushes, a water tank, two swiveling wheels, and a large airfoil. The position of the platform is controlled by changing the length of the two cables via winches. Once the cable winches are set at the top two corners of the building, the robot can clean the entire wall. What's unique about this system is that it is an under-constrained parallel robot, in that it only has two cables for 2 degrees of freedom. We use gravity as a third cable, which allows us to reach every point on the wall, but that comes at the cost of lower stability compared to robots with more cables. So we have several features to increase the stability of the robot. First, the counter-rotating brushes create a stable frictional force that helps us counteract some of the external forces. Second, we have a large airfoil on the back of the robot, which helps capture some of the wind forces and transform them into a force pushing the robot against the building. Third, we have a self-leveling rotational joint where the cables meet the platform. This should not be necessary in calm conditions because the low center of gravity will keep the platform oriented correctly. But in case of turbulence causing the cables to move around, this will help the robot stay horizontal at all times. Finally, we're using nylon ropes instead of metal cables. This provides a slight stretch that acts as a damping factor in the system and reduces vibrations. You can see on the next slide our rendering of the robot on the wall, with the airfoil on the back, the cables moving it around, the swiveling wheels supporting it against the wall, and the two large brushes cleaning the window.
The simulator we designed allows the user to select a custom region that they want to clean. After selecting the region, they will be prompted to choose a cleaning pattern, which is either a vertical up and down pattern or a side-to-side pattern. Once a cleaning pattern is selected, the robot then determines the path trajectory it will take and calculates the cable lengths needed for the robot to move. In the video, the robot has a start position at the coordinates 5, 10. It then moves to a start position of 8, 5, then cleans between the regions 8, 5, and 6, 2. In the video, you will see the robot using both cleaning patterns to clean this region. In addition to showing the plotted path, the code creates a data table showing every point the robot travels to and the cable lengths needed to travel there.
Now we come to the results section where we've done the workspace analysis. This robot has 3 degrees of freedom, 2 translational and 1 rotational. Cable-driven parallel robots, when under-actuated, allow a greater amount of workspace to be traversed. The lack of control in under-actuated dual-ascender robots, also known as DARs, leads to a lot of vibration during facade operations. This can be tackled using a flexible rope to model the vibration direction, natural frequency, and damping ratio into a Jacobian matrix and applying input shaping control based on the resulting model decomposition. One of the main advantages of a robot is that the moving pattern can be sideways too, which means the robot can clean buildings with holes and also ones that have a convex shape. Having a cable-driven robot also allows the robot to have high acceleration over a large workspace, which means quicker cleaning times. As far as the forward kinematics is concerned, we can clearly see that the two cables control the motion of the platform throughout the workspace. The change in the length of the cables moves the robot to different portions of the window. Similarly, for inverse kinematics, the movement of the robot between 2 points can be mapped out by considering it to be a function of the lengths of the ropes. 1 and 2 describe the position vectors, and the velocity in the joint space and the speed in the Cartesian space are proportional to the Jacobian matrix in equilibrium. Equation 3 and 4 demonstrate the relationship between the displacement in the Cartesian and joint space, whereas Equation 5 describes the change in tension, which is related to the external force when, in the steady state, the tension and the gravity balance out.
Currently, robots that clean windows attach to existing crane systems on buildings, which limit the robots to vertical movements only. Additionally, our robot can clean buildings that have more obscure geometries that traditional window cleaning systems struggle with. The proposed autonomous cable-driven parallel robot for cleaning skyscraper windows will improve work efficiency for building managers and maintenance staff. The setup costs are lower for a robot like ours, and the motion is overall more energy efficient. In addition, the payload capability is much more than a gantry robot because cable-driven systems are low weight, high strength. Our simulation shows that our robot arm is able to reach all desired locations in its workspace and can autonomously clean the full face of a building from top to bottom by planning a trajectory, then following the path in a horizontal or vertical pattern, as desired by the user. This presentation shows that we first created a robot with feasible link parameters with respect to the building environment. This was demonstrated through the 3D model of the building and the robot. The forward and inverse kinematics were calculated and simulated via MATLAB. After this was tested and verified, the workspace of the robot was calculated and plotted. A few improvements can be made to the robot as future extensions. For one, to improve the suction on dirty surfaces. Additionally, we can modify the robot to work on pointy buildings. Brushes may get damaged when rubbing against the concrete and metal panels supporting the glass, so maybe adding a computer vision system to only clean the window surfaces. Next, we could make cable movements more environment resistant so the robot can navigate even in high winds, snow, ice, and dust. A crane installation could also be made easier to provide a holistic solution to the building owners. And lastly, we can modify our design to support robots on two sides of the building using one crane.